What's up everybody, your boy here, back again for another scientific video. I have so much energy today because we are finally doing something that feels sciencey, okay? In the previous video, we made a fume hood. But let me tell you, I got tired of working with wood for about a week. It gets old very quick. Wood working for $2, Most importantly, we're going right off with a big bang. So, first thing we are making is refractory materials. What is a refractory? And no, before anybody gets any ideas, not the psychology kind of refractory. Refractories are materials that have a very high melting point or are extremely chemically resistant, such as tungsten or graphite or aluminum oxide or molybdenum, or however the fudge you say. But the refractory we are going to be making today is aluminum oxide, potassium metasilicate. Both of these things are used in forged linings. And that is because they have extremely high melting points and, I don't know, something else. They're not very soluble in water, except probably the potassium metasilicate. Anyway. And this is one of the many steps we need to be able to make a forge. Well, actually it's a foundry because we're melting metal, not forging it. Anyways, aluminum oxide has a melting point of 2076 degrees Celsius. And that's why whenever you see like refractory bricks and whatnot, they're going to be made out of aluminosilicate materials. And the fact that aluminum oxide is probably one of the higher up there refractory ceramics is kind of ironic to me because aluminum has such a low melting point. Potassium metasilicate that I will be making, on the other hand, is doesn't have quite as high of a melting point, and that's okay because it's mostly going to be used as a binder and to protect the concrete from water somewhat. Even though water glass is water soluble, it's okay. So for this video, we are going to be working with dangerous chemicals such as hydrochloric acid, one of my favorites. So if you didn't build the fume hood, go back to that video, build that, or something like it, or at least work outdoors. That's about all I got for a safety briefing. Alright, so now I'm going to go ahead and write out the balanced stoichiometric equation. All right, there's the balanced stoichiometric equation. Oh, that looks terrible. Okay. Obviously, with most aluminum alloys, you're not going to have 100% perfect aluminum, which is fine for the sake of us making a refractory. We're not trying to make synthetic corundum or anything in this video. So purity isn't exactly the most important thing right now. I mean, of course, you still want to try to keep it relatively pure, but it's fine, I promise. We're not going to die. The hydrochloric acid is going to turn the aluminum into aluminum chloride. It's a nice little salt, and it's also going to release hydrogen gas. Another thing it's going to release, it's not really written anywhere, is heckin' heat. Yeah. And that's why I'm using borosilicate lab glass, because it's very resistant to thermal expansion. Alright, now what I'm going to do is I'm going to weigh out my little aluminum ingot. Aluminium. I don't even know how you mess it up that bad. Where's the extra inium, anyways? Yes, 169 grams. Now that was completely pointless since I'm going to be eyeballing most of this. So, reaction time. Step 1. Place beaker in fume hood. Step 2. Add aluminium into the beaker. Now, as you'll notice,
I'm not wearing any gloves and I'm about to handle dangerous chemicals. Do you know why I'm not wearing any gloves? Because all of you freaking mouth breathers are buying them all. And they're not even using them right. Like, what is that? Step 3, turn on the fume hood fan. Step 4, add the hydrochloric acid. Should react very instantly. Hydrochloric acid acts very reactively with aluminum. Because aluminum will react with just about anything. Alright, we're going to leave that alone for a little bit while it reacts. In the meantime, dihydrogen monoxide. Alright, after leaving it for a little bit, it looks like not as much gas is evolving out of it. Some kind of froth is formed. So, we'll see what happens if I stir it up. I actually just got these in. My new borosilicate chemical stirrers, whatever they're called. Before I was using like plastic knives. It's not ideal. That's a little toasty. Man, it just eats this stuff. And my hands itching. Cool. Like with most things, this is the prime time to add some more hydrochloric acid. So I'm going to add in some more. Pretty quick reaction. 100 milliliters of hydrochloric acid was added in solution. Good lord, I cannot stand passive voice. Like, it's such a waste of time. Like, I wonder if the reason why there's no vaccine for COVID-19 yet is entirely because some dude out there is bitching and crying because some dude's citations weren't right or he didn't fully use the passive language all the way through. Like, dihydrogen monoxide. Alright, I'm getting pretty tired of babysitting bubbles. I'm going to add a little bit of concentrated dihydrogen monoxide. This does dilute the solution, yes, but it's still acidic enough to dissolve aluminum, as you can see. It's such a crappy metal. Alright, so another issue I started having while I was going through this reaction was that the production of hydrogen gas was bubbling up in this metallic paste right here. So I thought adding little bits of hydrochloric acid and just leaving it for a little while would work, but apparently that is not the case. And I think I also lost my Toastmaster thing. Oh well. Alright, the reaction's been going for about a day now. It's very minimal now. I don't know if you can see the bubbles. So I'm just going to go ahead and filter most of this off right here with an Erlenmeyer mask, essentially made out of a vodka bottle and a funnel. The friggin' filter. Just do this very slowly and carefully. Alright, we are now on the second pouring of everything. And our aluminum ingot has shrank a little bit. So after all this is done and said, I really want to make a determination of what all this black residue is. I have a couple of theories, but I'm not really going to dive into experimenting with that until maybe another video or later in this video, depending on how long it actually ends up being. So for right now, I'm actually going to try to have patience and slowly pour all this stuff in so it doesn't foam over and have to dilute it with water.
it's been a hot minute since I've touched everything. It took quite a while for all this stuff to filter through. So maybe in the next video I'll make myself an Erlenmeyer flask or something to help speed up the filtering process. As of right now though, here's our aluminum chloride solution. It's got some bullshit at the bottom of it. I'm not really gonna care for right now, just so I can get through it. I obviously have a lot of cleaning to do because that shit was messy as hell. But yeah, the next step is pretty straightforward. So to remove the chloride ion from the aluminum, we're going to be using sodium bicarbonate. It's freaking baking soda. All right, so now we're going to start adding in the sodium bicarbonate and try to add it in like little bits at a time because it will start to form up bubbles like, you know, vinegar and baking soda. Yep. All right, it simmered down a little bit, so I'm just going to give it a couple stirs. After playing around with this reaction a little bit more and adding some more baking soda, I got a consistency a lot more like what you would see if you were making aluminum oxide. This is this little paste right here. It's going to be thick, very hard to move and stir, and that's because aluminum oxide and the salt produced are both desiccants, meaning that they absorb water. So they've dehydrated it, meaning that there's no water. Just going to go ahead and start adding water to this one. Give it a good old stir. Yeah. Just going to go ahead and try to carefully pour off the water from this reaction. It'll let me, yeah, make a nice little hole. Oh, that feels so gross. The reaction on the left is now turning into yet another thick consistency. That looks like grits now. It must have been like dehydrated enough to where it wasn't reacting fully with the baking soda. And so giving in some more water probably helped a little bit. But now this shit is dummy thick. All right, now I'm at a point where I think I can actually start like washing off all the salt and stuff like that. So right here, how am I peeling? Oh, it's probably from touching all this shit. So at the top right here, that is a solution of water and salt. And right here is our aluminum oxide. I don't know if I talked through this earlier, but we're just going to do what's called canting off the water, which is where we just pour off this top portion. And where are all these bubbles coming from? Okay, so now that I've poured off the water containing the salt several different times, I'm going to go ahead and walk through what we need to... Why are you blue? Anyways, I'm going to go through the rest of how to do this. It should not be blue, it should be more clear, a lot like that. So the rest of this is going to be just me getting all the water out of here. Alright, so to drive out all the water, I'm pretty much just going to put this in my... Good lord, I need to clean my oven. It's a little mini oven. Just going to put this in here. And set it to 350. Big. And that should drive off most of the water. Yes, this is oven safe. Should be anything coming off of that that make it not safe. So once the reaction is done, you should end up with a powder like this. Just nice white fine powder. And this is our aluminum oxide. Now if you notice, there's little bits and pieces of impurities throughout it. And for the purpose of why we'll be using this, that's fine. I might wash this out a little bit more just to see if there's any salt left, but last time I checked, there's not.